Okay, so the example that we're going to work through is actually, this has come up a few times. A few people have asked me about, would you always use a Gaussian distribution as your prior, or are there scenarios in which you'd use a different distribution? And the answer is yes. And one other thing that I just want to, I might have this wrong, but let's all in the same room try to be wrong in the same way. So what I'm calling a prior is the distribution that we are inferring hierarchically. And what I'm calling a hyperprior is the prior one level above that, where we're not inferring anything, it's fixed, we are choosing a prior, a hyperprior, over our prior parameters. Okay, just because that might be backwards, but that's what I've been saying for this whole class, so let's stick with that. I think that's usually, like, I don't know, hyper means that it's above. I think that's probably right, but I'm not 100%. Okay, so in this problem set, we're going to infer distances to stars using Gaia data, just using parallaxes. And so I don't know if many of you have worked with Gaia data before, but you might have heard, if you do work with Gaia data, that if you want to calculate distances, it's best not to invert the parallax, not to do 1 over parallax, but to actually infer the distance using inference and a prior. And so that's what we're going to do. We're going to infer the distance using a prior. We're going to do it non-hierarchically first, where we use a prior that is motivated from physics. It is a model of the distances of stars in the Milky Way. And it's based on the Byler-Jones paper, which is, there's a link in the notebook. This notebook, by the way, is called Gaia_exercise. So we'll start with that, where we just have our prior. We choose, the prior only has one free parameter. In the first non-hierarchical version, we'll fix the prior. We'll choose a value for it. And in the second hierarchical version, we will infer the value of that parameter. These are simulated data. We're not using real Gaia data. So I simulated the data with a chosen value of L. L is the length scale of the prior. And at the end of the notebook, hopefully you'll be able to tell me, we might not get to the end, but if you do, you'll be able to tell me what value I used for L to simulate the data. Okay, so in the GitHub repository, there should be this notebook called Gaia exercise, and there's a CSV file called parallaxes. Hopefully you have the code, the beginning parts of the code in Gaia exercise. Hopefully I didn't accidentally put the solutions in there too. So the first few lines of this notebook go through just opening the data file, plotting. I've given you the true distances so that you can use to like check that you're doing things right. They're in the CSV file. Plotting 1 over parallax versus true distance. And then there are some stages that I'd like you to go through. I'd like you to draw the probabilistic graphical models. What do you think we're doing? You know, we have parallaxes, we have parallax uncertainties, we're trying to infer distance. The model is just the reciprocal of the distance. So it's a simple model. And the prior is in this paper. You can go and look it up. It's not particularly complicated. Like I said, there's one free parameter in it, L. And so draw the PGMs. I think going from the non-hierarchical version to the hierarchical version we covered. So hopefully that will be okay. Let me know if you have any questions. PyMC3 we'll use to define this model and do the sampling. This part, the prior, defining the prior is tricky. You need to use a PyMC3 potential. I will probably, don't worry too much if you get stuck on this bit. it's a little tricky. I'll probably put some code up on the screen in a bit because it's definitely not obvious. And the PyMC3 documentation isn't always like, for astronomy, isn't always the easiest to navigate. So I might help you with that bit. But at least try and sort of fill out, like what goes in the model, what goes in the likelihood, generally what's going to go in the prior. You can look up the functional form of the prior and you can write the code in there. Go back to this HBM lecture notebook, look at what I did in the PyMC3 section and try and sort of copy that over. And then in the first step, you'll do the non-hierarchical version and you'll try and infer a distance for each star. In the second version, you'll do it hierarchically and you'll infer a distance for each star and you'll infer L, the prior parameter. Okay, I think that's all I wanted to say. Are there any questions about this? Okay, so we're nearly at the end of our time. So just to reiterate again, what we've done here, the reason why this is different from the non-hierarchical version is just that we've added L into our inference process, and now there is a hyperprior over L. L was a fixed parameter, now it's a free parameter, and that's the only difference. Has anyone successfully managed to run the code and have an idea of what the value of L I chose is? You want to shout it out? Oh yeah. So you can make a histogram over the trace of L. And okay. Yeah. It's 500. So everything I heard sounded, well, you didn't give me error bars, but I know that the error bar is relatively big, so all of those values sounded pretty much good to me. So this is how you can make a histogram over your trace, and then you can, if you want to know a summary statistic, you can ask what the mean value is and the standard deviation of this distribution. And so there are some things about this exercise that I learned that are a bit confusing. So I'm sorry about those. R, so in the paper, R is used instead of D. I think that's kind of confusing, especially since I used R to convert D between kiloparsecs and parsecs. There are some, so using PyMC3 is a learning curve for me. There are some things that it does that I don't understand very well. And so I can't be very helpful for you, like really explaining the nitty gritty of what the potential object does here and why we're sampling from these uniform distributions and then applying the prior. Dan is an expert in PyMC3. So if you have questions about that, you can ask him. Sorry, Dan, I'm volunteering your services. What else did I want to say? This PyMC3 is unbelievably powerful, and that's why I wanted to use it, because it is so fast to sample many parameters, and without it, hierarchical inference is really difficult to practically implement. So PyMC3 is an incredible tool. I hope that you, at least from this session, can take away what hierarchical modeling is, and if there is a scenario in future in which you think it makes sense to use it, at least you have kind of seen it before and you have a basic understanding of kind of what it is.